The night sky above us appears peaceful, an endless canvas of twinkling stars that humanity has gazed upon for millennia. Yet hidden within that cosmic darkness are fragments of the solar system's violent birth, tumbling through space at velocities that defy comprehension. These are the asteroids, and among them exists the potential to rewrite civilization as we know it. The question that haunts planetary scientists today is not whether such an impact will occur, but whether we'll be ready when it does. The sleeping giants. Right now, as you listen to these words, more than 2,493 potentially hazardous asteroids have been catalogued by astronomers. These are the ones we've managed to detect. These cosmic travelers meet two unsettling criteria. They measure larger than 460 feet in diameter, and their orbits bring them within 4.6 million miles of Earth's trajectory around the Sun. To put that distance in perspective, while it sounds vast, in astronomical terms, it's barely a hair's breadth. These are the neighbors we need to keep our eyes on. Among these tracked objects, 155 span more than 1 kilometer in diameter. An asteroid of this magnitude striking Earth would cause devastation on a global scale, triggering mass extinctions and fundamentally altering the planet's climate for decades or centuries. NASA estimates that about 93% of these kilometer-sized behemoths have been found, but that still leaves potentially dozens of world-ending rocks floating in the darkness, undetected and unaccounted for. For the smaller but still catastrophic asteroids, those measuring around 140 meters across, the situation grows more concerning. These objects pack enough destructive force to devastate entire metropolitan areas, yet we've discovered less than half of them. The rest remain invisible, silent threats traveling through the void. The largest known potentially hazardous asteroid currently identified bears the designation 53319-1999 JM8. This mammoth rock stretches approximately 7 kilometers across, large enough to cause an extinction event rivaling the one that ended the dinosaurs' reign. Thankfully, calculations show this particular giant poses no collision risk for at least the next century. But the cosmos operates on timescales that dwarf human civilization, and what's safe today may become catastrophic tomorrow. When reality struck home. The morning of December 27, 2024, marked a watershed moment in planetary defense. The Atlas telescope system in Chile spotted something new, an asteroid designated 2024 YR4. Initial observations suggested this space rock measured between 40 and 100 meters wide, comparable in size to a 10 to 30-story building. Within days, automated warning systems flagged this object with alarming news. It had a non-zero probability of striking Earth on December 22, 2032. By late January 2025, that probability had crystallized into something far more concrete. Asteroid 2024 YR4 achieved a rating of 3 on the Torino Impact Hazard Scale, marking it as a close encounter worthy of serious attention from both astronomers and concerned citizens. At its peak assessment, this asteroid carried a 3.1% chance of collision, the highest impact probability NASA had ever recorded for an object of its size or larger. For the first time in the history of asteroid monitoring, humanity faced a credible, measurable threat that demanded coordinated international response. The scientific community mobilized with unprecedented speed. Telescopes around the globe swung into action, from the Magdalena Ridge Observatory in New Mexico to the Very Large Telescope in Chile's Atacama Desert. Each observation refined the orbital calculations, slowly painting a clearer picture of 2024 YR4's true path through space. The asteroid spun faster than typical rubble pile asteroids, completing one rotation every 19.5 minutes. Its composition appeared to be either skew-type or K-type, though even this classification remained subject to debate depending on which observational platform examined it. By early March 2025, enough data had accumulated to ease fears. Further observations determined that 2024 YR4 posed no significant impact risk in 2032 or beyond. The crisis, if it could be called that, had passed, but the episode served as Earth's first real-world planetary defense test, a rehearsal that revealed both the strengths and weaknesses of our detection and response systems. The International Asteroid Warning Network issued its first ever potential asteroid impact notification, putting the astronomical community on high alert and demonstrating that the protocols developed over years of planning actually functioned when tested against reality. The day the dinosaurs died. To understand the stakes of asteroid impacts, we must journey back 66 million years to a moment that changed the course of life on Earth forever. Picture a world dominated by giants, where Tyrannosaurus rex prowled steamy forests and pterosaurs soared through humid skies. The Cretaceous period was approaching its end, though no creature alive could have known what was coming. High above the atmosphere, an asteroid roughly 10 to 15 kilometers wide was hurtling toward Earth at approximately 20 kilometers per second, more than 58 times the speed of sound. This carbonaceous chondrite, a dark rock, rich in organic compounds, had originated from beyond Jupiter's orbit, traveling for millions of years before fate aligned its trajectory with our planet. When it struck what is now Mexico's Yucatan Peninsula, the impact unleashed energy equivalent to 100 teratons of TNT, or 4.5 billion, times the explosive power of the atomic bomb that devastated Hiroshima. The Chicxulub crater that formed spans 200 kilometers in diameter and reaches 30 kilometers deep into the Earth's crust, making it one of the largest impact structures ever discovered on our planet. But the crater itself was merely the beginning of the catastrophe. The asteroid vaporized upon impact, and the collision launched massive plumes of vaporized rock, sulfates, and debris high into the atmosphere. These materials spread globally, blocking out the sun and plunging Earth into what scientists call an impact winter. Temperatures dropped by as much as 50 degrees Fahrenheit as photosynthesis ground to a halt. Plants died, then the herbivores that depended on them, followed by the carnivores at the top of the food chain. Approximately 75% of all species on Earth vanished in the aftermath, including all non-avian dinosaurs. The rock layers from this period, found worldwide, contain elevated levels of iridium, a metal rare in Earth's crust but common in asteroids. This chemical signature serves as a permanent memorial to the day the sky fell. Recent drilling expeditions into the Chicxulub crater have revealed additional horrors from that ancient cataclysm. The impact vaporized massive deposits of sulfate-rich rocks, releasing these compounds as aerosols that lingered in the atmosphere for years or decades. Ocean acidification occurred rapidly, disrupting marine ecosystems and contributing to the mass extinction. The planet that emerged from this crucible was fundamentally different from the one that existed before, its evolutionary trajectory forever altered by a single cosmic collision. Thunder. Over Siberia. The early morning of June 30, 1908, dawned clear over the remote forests of central Siberia. Local indigenous Evenk people were beginning their daily routines near the Podkamennaya Tunguska River when the sky itself seemed to tear open. Eyewitnesses described a column of bluish light, nearly as bright as the sun, streaking across the heavens from the southeast. One survivor, a man named S. Semenov, recalled sitting outside when he suddenly saw the northern sky split in two, revealing fire high and wide over the forest. The heat became so intense that he felt as though his shirt had ignited. The asteroid, estimated at 50 to 60 meters wide, never actually reached the ground. Instead, it exploded in an airburst at an altitude between 5 and 10 kilometers, releasing energy equivalent to 3 to 50 megatons of TNT, or roughly 185 Hiroshima bombs. The shock wave radiated outward at supersonic speeds, flattening an estimated 80 million trees across 2,150 square kilometers of taiga forest. Near the epicenter, trees remained standing but were stripped of branches and bark, resembling a forest of telegraph poles. Further out, the blast knocked trees down radially, all pointing away from the explosion site like compass needles frozen in time. The remote location spared humanity from a true catastrophe. Had the Tunguska event occurred over London, it would have obliterated everything within the M25 motorway, killing millions. Over any populated area of the United Kingdom, tens of thousands would have perished. The sparse population of the Siberian wilderness meant that, apart from 2 or possibly 3 unconfirmed deaths and hundreds of reindeer, the impact claimed few victims. Yet the event sent seismic waves recorded by instruments in Western Europe, and the atmospheric disturbance caused abnormally bright nighttime skies across Siberia and Europe for weeks afterward. No scientific expedition reached the site until 1927, nearly 2 decades after the explosion. Russian mineralogist Leonid Kulik led the first team through the difficult terrain, finding ample evidence of the asteroid's destructive power despite the passage of years. The lack of any impact crater puzzled investigators for decades, fueling wild speculation about alien spacecraft and antimatter. The truth proved more mundane but no less sobering. Tunguska represented an air burst from a relatively small asteroid, the kind of impact Earth can expect on average once every century. We've been lucky that subsequent Tunguska-scale events have avoided populated areas, but that luck cannot hold forever. The meteor the cameras caught. February 15, 2013 began as an ordinary Friday morning in Chelyabinsk, Russia, a city of more than 1 million people in the southern Urals. At 9:20 local time, that ordinariness shattered. An asteroid approximately 20 meters in diameter, weighing 9,100 tons, entered Earth's atmosphere at a shallow 18-degree angle, traveling at 19.2 kilometers per second. The object had approached from the direction of the sun, hidden in its glare, giving absolutely no advance warning to the people below. For several seconds, the meteor blazed across the sky, creating a light show captured by dozens of dashboard cameras throughout the region. Russian drivers commonly install these cameras to document traffic disputes, but on this day, they recorded history. The footage shows a brilliant streak of light growing brighter and brighter until it briefly outshines the sun itself. Then, at an altitude of approximately 30 kilometers, the asteroid exploded. The air burst released energy equivalent to 440,000 to 500,000 tons of TNT, roughly 30 times more powerful than the Hiroshima atomic bomb. A searing flash lit up the morning sky, visible from 100 kilometers away. Eyewitnesses reported feeling intense heat from the fireball despite the frigid February temperatures. But the most destructive element was yet to come. The shockwave, traveling more slowly than the light, arrived minutes later. Many people, curious about the bright flash they'd witnessed, went to their windows to look outside. The delayed shockwave shattered those windows, sending thousands of glass fragments flying inward at high velocity. Over 7,200 buildings across 6 cities suffered damage. Approximately 1,500 to 1,600 people required medical attention, with injuries ranging from minor cuts to severe lacerations. Remarkably, no deaths were reported, but the psychological impact rippled through the region. This was the largest asteroid impact on a populated area since 1908, and it struck without any warning whatsoever. The Chelyabinsk event revolutionized scientific understanding of asteroid airbursts. Researchers at Lawrence Livermore National Laboratory spent years creating high-fidelity 3-dimensional simulations of how the meteor fragmented and deposited its kinetic energy into the atmosphere. The wealth of video evidence captured from multiple angles by everyday citizens provided data that would have been impossible to gather from any planned experiment. Scientists learned crucial details about material strength, fracture patterns, and the breakup dynamics of small asteroids entering Earth's atmosphere at hypersonic velocities. Perhaps most troubling, the Chelyabinsk meteor demonstrated our detection gaps. Objects of this size approach Earth with disturbing regularity, perhaps once every 60 years on average, yet we have no reliable system for spotting them in advance. Ground-based telescopes excel at detecting asteroids approaching from the night side of Earth, but objects coming from the direction of the sun remain effectively invisible until they're already here. The Chelyabinsk wake-up call spurred renewed investment in detection systems and planetary defense strategies, but significant blind spots remain. Standing guard. In response to growing awareness of the asteroid threat, NASA established the Planetary Defense Coordination Office in 2016. This office coordinates detection, tracking, and characterization of potentially hazardous near-Earth objects, issues warnings about possible impacts, and assists in planning the government response to an actual impact threat. The office represents humanity's first organized attempt to protect the planet from cosmic collisions, moving planetary defense from the realm of science fiction into practical policy. On September 26, 2022, planetary defense took a giant leap forward. NASA's double asteroid redirection test spacecraft, traveling at approximately 22,530 kilometers per hour, deliberately crashed into an asteroid named Dimorphos. This small moon, just 160 meters in diameter, orbits a larger asteroid called Didymos in a binary system. Neither asteroid posed any threat to Earth, making them ideal candidates for humanity's first attempt to alter a celestial body's trajectory. The impact succeeded beyond expectations. Before DART struck, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After impact, that orbital period shortened to 11 hours and 23 minutes, a change of 32 minutes. This reduction far exceeded NASA's minimum success threshold of 73 seconds. The deflection wasn't caused primarily by the spacecraft's momentum transfer, but rather by the recoil effect of debris ejected from the impact site. Thousands of tons of asteroidal material blasted into space, effectively turning Dimorphos into a momentary rocket and amplifying the deflection. The DART mission demonstrated conclusively that kinetic impactor technology works. If astronomers detect a threatening asteroid decades before potential impact, we now know that crashing a spacecraft into it can alter its orbit enough to make it miss Earth entirely. Even a small change in velocity, applied years in advance, translates into a missed distance of thousands of kilometers by the time the asteroid reaches Earth's orbital neighborhood. The key word here is advance. Deflection requires time, ideally many years or even decades of advance warning. An asteroid detected mere months before impact presents a far more difficult problem with potentially no viable solution. The European Space Agency's Hera mission, launched in October 2024, will conduct follow-up investigations when it reaches the Didymos system in late 2026. Hera will examine the crater DART created, precisely measure Dimorphos's mass and internal structure, and help scientists understand exactly how the kinetic impact technique works under real-world conditions. This knowledge will prove crucial for future planetary defense operations, allowing mission planners to predict deflection outcomes with greater accuracy. The God of Chaos approaches. On April 13, 2029, an asteroid named Apophis will pass closer to Earth than many of our communications satellites. The date alone seems ominous, Friday the 13th. The asteroid's name, drawn from the ancient Egyptian deity of chaos and darkness, feels equally foreboding, yet there's no actual danger. Current orbital calculations, refined over 20 years of observations and radar tracking, show that Apophis will safely pass at a distance of approximately 31,600 kilometers above Earth's surface. That's about 1/10 the distance to the Moon, or roughly 5.9 Earth radii. When Apophis was first discovered in June 2004, the story was very different. Initial observations suggested a 2.7% probability that it would strike Earth in 2029, earning the asteroid a rating of level 4 on the Torino scale, the highest threat level ever assigned to any near-Earth object. For a brief period, Apophis seemed to represent an actual existential threat, an asteroid capable of regional devastation that might actually be on a collision course with our planet. Scientists named it well. Additional observations gradually reduced the impact probability to zero, at least for the foreseeable century. The 2029 flyby will be extremely close, but completely safe. However, this proximity offers an unprecedented scientific opportunity. Apophis measures approximately 340 meters in diameter, making it large enough to cause significant regional damage if it ever did strike. A close approach by an asteroid this size occurs only once every 7,500 years on average. During the flyby, more than 2 billion people across Europe, Africa, and Western Asia will be able to watch Apophis with the naked eye, appearing as a bright point of light moving steadily across the night sky. Earth's gravity will physically reshape Apophis during the encounter. Tidal forces will stretch and squeeze the asteroid, potentially triggering landslides on its surface and changing its rotation rate. These gravitational interactions might even cause internal seismic activity, offering scientists a chance to peer inside an asteroid for the first time. NASA's OSIRIS-APEX spacecraft, repurposed after successfully collecting samples from asteroid Bennu, will rendezvous with Apophis before the Earth encounter to observe these changes up close. The European Space Agency's proposed Ramses mission aims to accompany Apophis through the flyby, documenting how our planet warps and alters this ancient fragment of the early solar system. The 2029 encounter will also shift Apophis's orbit permanently. Currently classified as an Aten asteroid, with an orbit smaller than Earth's, the gravitational slingshot effect will widen its path around the Sun, reclassifying it as an Apollo asteroid. Nature itself will conduct an experiment in asteroid dynamics, and humanity gets a front-row seat to observe every detail. The gaps in our shield. Despite remarkable progress, significant vulnerabilities remain in our planetary defense capabilities. The recent 2024 YR4 incident, though it ended without incident, exposed weaknesses in detection timelines and response coordination. The asteroid was discovered less than a month before it topped the risk lists, and observational windows proved frustratingly brief before the object moved too far from Earth for detailed study. If 2024 YR4 had maintained a significant impact probability, the limited observation time before it disappeared from view would have left dangerous uncertainties in our understanding of the threat. Smaller asteroids, those in the 20 to 50 meter range like the Chelyabinsk impactor, remain largely invisible to current detection systems. These objects are too small to cause global catastrophes, but large enough to devastate cities if they happen to strike populated areas. The Nuclear Test Ban Treaty Organization operates infrasound sensors that have detected 26 asteroid impacts, releasing atomic bomb-scale energy since 2000, suggesting these events occur far more frequently than most people realize. The difference between a Chelyabinsk-scale disaster and a much worse outcome often comes down to pure chance. Whether the asteroid strikes land or ocean, a city or wilderness, asteroids approaching from the direction of the Sun remain particularly problematic. Ground-based optical telescopes cannot observe the day side of Earth's neighborhood effectively, creating a blind spot that Chelyabinsk exploited. Space-based infrared observatories like NASA's NEO Surveyor, currently in development, should help address this gap when they launch, but they remain years away from operation. Perhaps most concerning is the response time problem. Even if we detect a threatening asteroid decades in advance, deflection missions require years to plan, build, and launch. The DART mission took years of preparation for a target that posed no actual threat, conducted under optimal conditions with unlimited time. A real planetary defense operation would need to proceed on a compressed timeline, potentially with fragmentary data about the target asteroid's composition, structure, and rotation. These unknowns could make deflection attempts less predictable and potentially less effective. The questions we must answer. Humanity stands at a crossroads in its relationship with the cosmos. For the first time in our species' history, we possess both the technology to detect incoming threats and the capability to potentially deflect them. But technology alone is insufficient. We must build robust international frameworks for information sharing, decision-making, and coordinated action. Who decides whether to attempt a deflection? What if deflecting an asteroid away from one region puts another at risk? How do we communicate uncertain but potentially catastrophic risks to the public without causing panic? The 2029 Apophis flyby offers a dress rehearsal for these questions. International space agencies and astronomical organizations are coordinating observation campaigns, sharing data, and practicing the protocols that would govern a real emergency. The Space Missions Planning Advisory Group, convened by the United Nations, provides a forum for nations to collaborate. On planetary defense planning, the International Asteroid Warning Network facilitates rapid communication when new threats emerge. These institutions remain young and untested, but they represent humanity's best hope for a coordinated response if the day comes when we face a real impact threat. We cannot predict when the next Tunguska-scale event will occur, or whether it will detonate over a forest or a metropolis. We don't know which of the undiscovered, potentially hazardous asteroids will eventually cross our path, or when. What we do know is that impacts have shaped Earth's history, and they will continue to do so. The question is whether we'll be passive victims of cosmic chance or active participants in our planet's defense. The asteroid that could destroy humanity exists, tumbling through space on a trajectory we haven't yet mapped. Perhaps it won't arrive for centuries or millennia. Perhaps it's already on its way, hidden in the sun's glare or lurking among the millions of undiscovered objects smaller than our detection thresholds. We cannot prevent all possible impacts, but we can tip the odds in our favor. We can find more asteroids, characterize them better, and develop more effective deflection techniques. We can build the institutions and protocols necessary to mount a coordinated global response. We can turn our gaze upward, not in fear, but in clear-eyed determination to protect the only home we have. The night sky remains as beautiful as ever, its stars twinkling with ancient light. But now we know what's out there in that darkness, and we're finally beginning to prepare. Whether that preparation proves sufficient remains the greatest test humanity may ever face. If you've found this exploration of planetary defense valuable, subscribe to see more deep dives into the questions shaping our future. And remember, when you look up at the stars tonight, you're not just seeing beauty. You're seeing our cosmic neighborhood, and some of those neighbors deserve very close attention.